So the second derivative test could help us find local extrema as well. The only problem is that sometimes it's not the best method because it leaves us without all the information. So let me give you guys the idea of how it works. I'm going to draw 3 pictures here. Actually, let's do 4. Okay, so I'm going to draw one with a minimum, another with a maximum. I'm going to draw one that looks kind of like x cubed, and then I'm going to draw this one as sort of a prolonged maximum. Okay, so notice how all of these have a critical point, each one of these. Now the way the second derivative could help you is here, for example, notice that since it's concave up, that means the second derivative is going to be positive. Well, if you have a critical point and the second derivative is positive, well, that means that it has to be concave up. And so anytime you have a critical point and the second derivative is positive at that point, no longer having to test around the point, simply at that point, then you're going to have a local minimum. So this would save you some time because you don't have to test around it, only at the point. Now, the same thing applies for this point, for example, because you have a another critical point, and the second derivative here is negative because it's concave down. And so when you have the second derivative is negative at a critical point, then you would have a local maximum. Okay, so sounds simple, right? Well, the problem is that you have situations, and there's a couple of examples, where you get that the second derivative is equal to 0. And that doesn't mean that it's neither. It means that it's inconclusive. So in this case, if it's inconclusive, then you have to do the first derivative test anyways. So then you end up going back to the first derivative test. So it's sort of, there's pros and cons. It could save you some time because there's less numbers to plug in, but if it's inconclusive, you have to do the first derivative test anyways. So let's do an example. So let's do the second derivative test to find the local maximums for and minimums for this function. So the steps are, we start off the same way. We have, we're going to find the critical points. So we find the derivative, first derivative, which is 12x to the third minus 24x squared plus 12x. Okay, so we set this equal to 0, and we solve it. So we'll factor out a 12x, and that'll leave us with x squared minus 2x plus 1 is equal to 0. And we can factor this one more time into x minus 1 times x minus 1 equals to 0. So then what we have for our critical points is we have x equals to 0, and then we have x is equal to 1. Okay, so once we found our critical points, then we plug in critical points into the second derivative. And so let's do a little if here. If the second derivative is positive, that means that it's going to be concave up, which means it's a local minimum. And if the second derivative is negative, that means that it's going to be concave down, which means it's going to be a local maximum. And if the second derivative is equal to 0, this is bad news. This is inconclusive. Okay, so let's find the second derivative then. So the second derivative is equal to, I get the derivative of the first derivative, so that would give me 36 x squared minus 48x plus 12. Okay, so let's plug in 0. So if I plug in 0, I get 36 times 0 squared minus 48 times 0 plus 12. That equals to positive 12. So that means that x equals 0 is a local minimum from this one. And then to find the y value, of course, remember you plug in the x value into the original function. And if you plug in 0 into the original, you would get y equals to 0. So the point 0, 0 is a local minimum. Okay, and then if I plug in 1, so f double prime at 1 is 36 times 1 squared minus 48 times 1 plus 12. And 36 minus 48, that's negative 12 plus 12. Uh-oh, 0. Bummer. Inconclusive. Okay, so this is the worst case scenario, inconclusive. You know, I can't tell you how often this is going to happen if you try it, but happens often enough. So, okay, so if it's inconclusive, remember that what we need to do in that case is the first derivative test. Now, the good thing is that we don't have to do the first derivative test on the entire thing, only on that value. So here, let me do my number line. I'll put my critical points anyways, but I don't really care about 0 right now. I already know that there's a local minimum there, so I don't have to worry about that one. The one I do care about is 1 though. So I'm going to pick 2 points. I'm going to pick 1/2 and 2 to plug in. And now here, these I'm going to plug into the first derivative. Okay, so the first derivative, which is, I'm just going to use this one right here. Okay, so hopefully you remember how to do this. If you plug in 1/2 into this one, you're going to get a positive number. So that means that here it's increasing. And if you plug in 2, you're going to get another positive number, which means it's also increasing. So that makes sense that it was inconclusive there, because it's not actually a maximum or a minimum. So it's just a flat spot. Basically, it just means it's going up, flat, and then going up again at 1. So that's it.